Hello, hello. Got two more concepts to talk about before wrapping up our section on probability. One concept we're going to cover in this section is permutations, and then we're going to talk about combinations in the next section. So these are fun. Get to talk about, have all kinds of cool word problem type examples. Now, the first thing we're going to address, though, is something called the counting principle, which should look familiar to you because we did this in a prior lesson. Way back several lessons ago, we talked about how if you're wanting to see multiple experiments be performed and you want to see how many different ways can their possible outcomes turn out, you can use the counting principle to figure that out. The example I used when going over this was trying to pick out an outfit. Like if you wanted to see, well, how many different outfits are possible when you're getting ready in the morning, you take how many tops, how many bottoms, how many types of shoes, and you multiply those numbers together to see all the possible outfit arrangements. And that process is called the counting principle. And it turned out to be a rather large number. And of course, we weren't worried about details like matching. We didn't worry about undergarments and all that. If you start including undergarments and things, then your numbers get higher because you start multiplying by more values. Because you're taking everything that you're taking into consideration, you have to multiply the number of outcomes for each together. And that'll tell you all the arrangements. And then we use the counting principle after that to figure out, well, how many points would be in the tree diagram set. Like when you're done doing a tree diagram and you're getting a sample space, well, how many sample points are going to be in that sample space? The counting principle can help you to figure that out. Like, having 3 kids and trying to figure out how many arrangements of boy and girl can you have with 3 kids. Well, we figured out, each kid, there's 2 outcomes, boy or girl, and then you multiply 2 for the first kid times 2 for the second kid times 2 for the third kid. 4 times 2 is 8. You get 8 possible sample points there. You can do a tree and find those sample points for that entire sample space. So we're just revisiting that. That's all we're doing here. Nothing new, brand new right now with the counting principle. Just revisiting that concept. And I figured I'd revisit it with a couple more example problems, just refresh your memory, because the counting principle is going to be a key element of understanding permutations. All right, so let's look at an example. Oops, sorry about that. Let's look at an example where we're dealing with ATM codes. I think most of us have used an ATM at some point in our lives now. They're a pretty common thing. Like if you go to the bank, they're more and more they're wanting you to use the ATM machines instead of a banking associate. All right, so to use an ATM machine, there's one that you might have to enter a 4-digit code, 4-digit PIN. And you can, when you make up your digit, you can use digits, when you make up your PIN, you can use digits 0 through 9. So how many pins are possible? If repetition is permitted. Okay, we're not going to go through and list all the pins. We're just going to see, well, if you did do a sample for a tree and found the sample space, how many sample points would there be? How many pins could you list that fit these requirements? Okay, so it's a 4-digit PIN. So when you go to type in your PIN number, it's kind of redundant to say PIN number because N stands for number in there anyways. PIN is personal identification number. So when you go to type in your PIN, you put a number here, you put a number here, you put a number here, you put a number here. Each of these blanks has to have some digit 0 through 9. And since they're allowing repetition, your PIN can be 4 of the same number. It can be 9999, 2222. But it can also all be different. It depends on what you want. So you look at, okay, in the first input, I have 10 options. So that 10 isn't the number for my PIN, it's just how many options are there for that first digit. Because I can use anything from 0 through 9. And since repetition is permitted, I can again use anything from 0 to 9 on that second part of the PIN, and on the third, and on the fourth. And by the counting principle, it says take all of those numbers and multiply them together. 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. And there you go. Wow, that's a lot of pins. But heck, if you have a computer that can go through and start guessing, it probably wouldn't take it very long to generate all 10,000 of those. And that's why, like, when you're making a password for something, they usually say, make it at least 6 characters, and they say use at least one in lowercase letter, one uppercase letter, and like use one of like 3 different things, a number, possibly a special character. They want you to increase the number of possible entries for each of these characters, because the more options you have, the bigger the number here when you're done, the bigger the number of possible passwords. So the more passwords possible there are, the harder it is for somebody to guess what your password is. Okay. All right, let's go on to passwords. Thinking about passwords here. Well, actually, let me review the outfits thing again. I did an example like this previously, and I just talked about it a second ago, but let me go through this one. Let's say you have 3 ties, 4 shirts, 2 pairs of pants. You have to pick one of each. How many different outfits are possible? So this is not quite as extreme as the example I did previously. Numbers aren't as big. Okay, so first blank you put the number of ties, which is 3. Second blank you put the number of shirts, which is 4. Third blank you put the number of pants, which is 2. And you multiply those together by the counting principle. 3 ties to choose from times 4 shirts to choose from times 2 pants to choose from gives you 24 different possible outfits. You could, if you did your tree, you'd have 3 branches for the ties. Then off of each of those ties, you'd have 4 branches for shirts. And then off of each of those shirts, you'd have 2 branches for pants. So you'd end up at the end with 24 sample points. All right, let's do another example with the counting principle. Passwords. Mentioned passwords a little while ago. Let's say a password can consist of any 4 digits or letters. Okay. Determine number of passwords possible. If A, letters are not case sensitive. So a lowercase letter counts the same as an uppercase letter. Also, it's important to note, repetition is permitted. That makes a difference. If repetition is not permitted, that makes a difference too. All right, repetition is permitted. Okay, so we have your password has to have 4 characters. When they say letters are not case sensitive, then a capital A is the same as a lowercase a. So we just consider the alphabet to be 26 letters. So we have digits 0 through 9. That's 10. You have 10 possible digits plus 26 letters gives you 36 options for that first entry. And since repetition is permitted, then those same 36 options are available in the second entry, the third entry, and the fourth entry. Okay, so you multiply all those together. Essentially, you have 36 to the 4th power, and you see what you get. 36 to the 4th power, and I get 1,679,616. Okay, what about option B? Letters are case sensitive. In that case, uppercase and lowercase letters are considered differently. So your lowercase letters, there's 26 of those. Uppercase letters, there's 26 of those. Plus you have your 10 digits, 0 through 9. So now, you have 26 lowercase plus 26 uppercase is 52, plus your 10 digits gives you 62. Oh, this is starting again. Stupid thing where it's jumping. I'm not even, all I'm doing is lifting my pen. All right, 62 to the 4th power, which ends up being 14,776,336. Wow. Okay. So there's some examples with your counting principle, how you can apply that. Now I have one more example of the counting principle. This one's also going to lead us into talking about something called permutations. We have 5 shapes. Circle, square, triangle, pentagon, and half circle. And we want to see how many different ways can the figures be arranged from left to right. Like how many ways can you line them up? Okay, this is essentially a counting principle problem. Because you're trying to line up these figures from left to right. So you got, I'm going to put 5 blanks because you could put, start lining them up in the blanks. When you go to line up the figures, when you go to put the first figure down here on the left, you have 5 options to choose from. Sorry about that, it was my other computer. Once you've put a figure down and you're lining these up, you can't use that figure again. So when you go to choose the figure that goes next in line, you've got 4 to choose from. And once you put that figure there, you're not going to pick it up and put it somewhere else. You're trying to line them up. So those 2 are out, leaves you with 3 choices here, 2 choices here, 1 choice there. So like right now, the arrangement up here is one possible arrangement. Circle, square, triangle, pentagon, half circle. When I go to put the first shape down, I could choose any one of those 5. But once I put one of them down, I've then got 4 of these to choose from. Next, I've got 3 to choose from, then 2, then 1. But I can multiply these numbers together to see, well, how many ways can I line them up? 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is still 120. So there I am. I have 120 ways I can line up those figures from left to right. And that's it. Well, it turns out that this particular problem that I use the counting principle on is also an example of something called permutations. A permutation is an arrangement of items where order matters. So, we're lining up those shapes. The order we're lining them up in matters. If I put circle first, square second, that's different than putting square first, circle second. If you switch the order around, then it's a different lineup. So if you want to see how many ways you can do that lineup, then you're doing something called a factorial. For however many items, in this case 5, so for n items, for 5 items, like we just did, the number of permutations is 5 factorial. That little exclamation point doesn't mean I'm shouting at you or excited about it. No, it's something called factorial in mathematics. And what factorial means is that you're taking your number and multiplying, your number is going to be a positive integer or like a nice natural number, and you're multiplying by all the natural numbers below it down to 1. So like the problem we just did, we essentially did 5 factorial, which is 5 times 4 times 3 times 2 times 1. So you start with that number and you do all the natural numbers below it until you get to 1. You multiply them all together, and in this case, we got 120. And that's how you figure out how many ordered arrangements of items are possible. So when you're lining stuff up, when order matters. All right, now you can do that factorial on a calculator. So let me pause this show for a second and pull up my calculator for you. Oh, there it is. Phew, I know I said to keep the writing. All right. This is an example. This is a TI-84, but your graphing calculators are similar. If you have a scientific calculator, you should see a button somewhere with a factorial. But on the graphing calculator, if I want to do 5 factorial, I can type 5, and then I can go to the math menu and see how it says math, num, CPX, which stands for complex, and PRB. PRB stands for probability menu. So we use our arrows and go over to the probability menu, and it gives us a bunch of options dealing with probability problems. And number 4 there has the exclamation point we need for factorial. You can either type the number 4 or you can scroll down to 4 and hit enter. And it puts that exclamation point in for you. Hit enter, and there's your answer. So the calculator will do a factorial for you. It's very helpful. Otherwise, you have to type in 5 times 4 times 3 times 2 times 1. And if you have something big like 72 factorial, you don't want to do that by hand. Calculator is useful. So you can do 72 exclamation point and enter, and there you go. Scientific calculators should also have the factorial option. If you don't immediately see it on your keys, refer to your manual or go online and do a search for your calculator and how to do factorial. It's either on a key right there or it's hidden in a menu, much like the graphing calculator menu, some kind of math menu or probability menu. But you should be able to do it. It's a pretty common function. All right, so now going back to our slideshow, let's go ahead and see about continuing with more examples of permutations. Okay, so what do we got next? All right, color wheel. We have what, Roy G. Biv on the colors. Let me change. I have to every time it reverse back to red. So I'm going to change it to black. Okay, if you're talking about the color wheel, red, orange, yellow, green, blue, violet, Roy G. Biv. I guess there's an indigo sometimes on the end of that too, but we'll just stick with Roy G. Biv. All right, how many permutations are possible from these colors? How many permutations of these colors are possible? Right now I have them lined up like the rainbow. But what if I want to see other lineups like red, yellow, orange, green, blue, violet, or green, orange, yellow, violet, blue, red? You know, I want to see other arrangements of these, and I want to figure out how many permutations are possible. Well, there's 6 colors here that I'm trying to figure out the arrangements, and since it's asking for permutations, that tells me order matters. So to find it, I do 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. And notice that that's the same result as the counting principle. There's 6 possibilities for the first entry, 5 possibilities for the second entry, 4, 3, 2, 1. Multiply them together. 6 times 5 is 30, times 4 is 120, times 3 is 360, times 2 is, what, 720, times 1 is still 720. Did I get that right? Yeah, so you have 720 possible permutations. So notice permutations can be found using the counting principle. But not all counting principle problems are permutations. Now, the counting principle can be found when you're just trying to figure out, well, how many different ways can something be done? But permutations are very specifically looking at ordered arrangements of objects. So, like if you're trying to find a password where repetition is permitted, that is a counting principle problem, but not a permutation problem. Because if repetition is permitted, it's not like you're really lining them up, because you're able to use the same ones over and over again. But if you're trying to find a password and repetition is not permitted, then that is a permutations problem, because then you're just like once you've used something, you can't use it again. It's like lining up stuff. You're lining up stuff. Once somebody's in line, they're not going to get out of line and go to another spot in line simultaneously. We're not getting into quantum physics here. We're just staying in our world at this level. So it all depends on how the counting principle problem is set up as to whether or not it's also a permutations problem. So permutations, you're dealing with arranging things where order matters, and the same item can't be repeated in the arrangement. So that's how you distinguish whether it's definitely permutation or not. But all permutation problems can be solved using counting principle. Sometimes when you're trying to find permutations, you might not need to use all the objects. You might only need to choose some of them. Like the example I give here, let's say you have a class of 25 students. You might ask, well, how many ways can we line up all 25 students? That's a permutations question, and you'd answer it by finding 25 factorial. 25 times 24 times 23, blah, 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 all the way down to 3 times 2 times 1. And that would tell you how many different ways you can line up the 25 students. But let's say you are holding elections for officers, class officers, like president, vice president, and secretary. You're choosing 3 students. Well, the same student can't hold 2 offices. You can't have the same person be president and vice president. You have to pick 3 separate students, and you want to see how many ways you can do this. And all 25 students can equally be selected for those offices. So when you go to select your office, your first selection, your first vote, you've got 25 students to choose from. And we're assuming all 25 are running for office, for any offices that are available. So when you go to pick your first one, for president, let's say, you've got 25 students to choose from. But once you pick your president, you can't use them again. So for VP, you've only got 24 students to choose from. Notice how I'm setting this up like a counting principle problem. Then finally for secretary, for president and vice president cannot be chosen for secretary, so you've got 23 students left to choose from. And you multiply 25 times 24 times 23, and you see just how many different ways you can pick 3 students to be officers for the class. And it looks like I just put my calculator and there's 13,800 ways to do this. That's quite a few. Now I did this using counting principle. But this is also a permutations problem because you are dealing with ordered arrangements. Who's president, who's vice president, who's secretary matter. If you switch Susie from president to secretary, that's a whole different thing. But you're only choosing 3 this time, so you can't just say 25 factorial. So notice that's not just 25 factorial, it's whittled down to 25 times 24 times 23. You're ignoring 22 down to 1. So the formula has to be updated a little bit. The formula for the number of permutations when you have n objects and choose R to get that result looks like this. NPR, no, it's not a radio station, not National Public Radio, but permutations of n objects choose R number of them. You see the n factorial up top here, and that was what we worked with before. And then on the bottom, notice that you see n minus r factorial. So these two numbers get subtracted, and you put that factorial on the bottom. Visiting our previous example, we had 25 students, and we're choosing 3. Okay, so in our example here that we just did on the other slide, we had 25 students, and we were choosing 3 for office. So according to this formula, we should do 25 factorial. You're like, Ms. Schofield, you said I didn't have to do that. Hold on. 25 minus 3 factorial goes on the bottom. But watch what happens here. You've got 25 factorial over 22 factorial. And still you might be like, but still, what about that 25 factorial? Don't worry about it. Watch what happens when I write this out. 25 times 24 times 23 times 22 times 21. I don't feel like writing anymore, so I'm going to shortcut times 3 times 2 times 1. You can use like this little ellipsis thing in the middle to say, hey, it keeps going in that pattern and then ends like this. Well, on the bottom, 22 factorial is 22 times 21 times 20 times 19 times 18, etc., down to 3 times 2 times 1. Well, here we are. Notice that the numerator and denominator have tons of common factors. And when you're reducing a fraction, you reduce common factors and see what's left over. Well, the 22 over 22 reduced down to 1. 21 over 21 reduces down to 1. As do all of these other numbers. They're the same. It's going to reduce down to 1. Leaving you with 25 times 24 times 23. Leaving you with the 13,800. Just like the counting principle. So notice that the permutation formula gives the same result as the counting principle. Like this right here was the counting principle result. There you go. Same as the counting principle right here, 25 times 44 times 23. But this formula can get you there. And you know how earlier I showed you on the calculator how you can do factorials on the calculator? Well, if you have a scientific calculator with statistics functions, you can also do permutations and later combinations on your calculator. Yes, I want to keep my annotations. Let's pull up the calculator and see. All right, let me clear what I already had there. Hang on a second. I keep losing my mouse. I have to turn it off and back on to make it work again. All right, let's clear the calculator. I have to do 25p3, like 25, choose 3. So I type 25. And remember that math menu on the graphing calculator? I can go over to PRB. And yeah, here's that trusty factorial. But instead, look at number 2. NPR. That's what I need. Permutations formula. 25, choose 3. And then enter. There I am. There's my 13,800 I needed. Isn't that amazing? There it is. So you can use your calculator's formula to make things a lot faster. Very handy. All right, let's turn this back into a full thing here. Okay, let's do another example with permutations. Skiing event has 16 participants for slalom. It keeps changing my pointer back to red. I don't want red. I don't want to be like shouting at you guys. Or red's like I'm grading papers or something. All right, 16 skiers for slalom. Top 5 by speed will be listed on a board. Now we haven't had the competition yet to see who were the top 5, who were the fastest. You know, first place, second place, third place, fourth place, fifth place. And they're going to be listed in order. Fastest to slowest. So how many ways are there for the 5 names to be listed? So since order matters, if you're in a race, order matters. Who comes in first is different than who comes in second, different than who comes in third, etc. So we're in a race, the order matters, and you're trying to look at, you've got 16, but you're only choosing the top 5 to go on this board in order. So you're trying to see how many ways that's possible before this race ever starts. So you've got all 16 right now who could potentially be on that board, and you're trying to see, well, how many ways can 5 of those end up on the board? 16, choose 5. So you got 16 factorial in the numerator, and then 16 minus 5 factorial in the denominator. So 16 factorial over 11 factorial. Well, 16 factorial, you got 16 times 15 times 14, etc. And I'm running out of room. You know what? Let me erase that and then continue it further down, because I don't want to run out of room. I want to write it all out and show you exactly how this ends up. I'm going to show you exactly how everything reduces. So even though you have your calculator and don't need to be doing this by hand, I still want to show you how it works. I want to show you how to reduce everything down and why it ends up, again, why it ends up being basically your accounting principle. So you have 16 times 15 times 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's the numerator. The denominator, you got 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So All of these are common, have common factors with each other. You got 11 over 11, 10 over 10, 9 over 9, etc. All that reduces down to 1, leaving you with 16 times 15 times 14 times 13 times 12. Which, if you're doing the counting principle, you would have had first place, you had 16 possible contenders. Second place would have had 15, third place 14, fourth place 13, fifth place 12. So you multiply that together, 16 times 15 times 14 times 13 times 12, and you get 524,160. So as far as how that leaderboard could end up being written there, you've got 524,160 ways that can turn out. That's quite a few options. That's a lot. But yeah, order mattered. We had 16 contenders. Only the top 5 are chosen. Okay. What else we got here? I think that's all the examples I want to do of just general permutations. There's one more special case I want to talk about, and that's permutations of duplicates. When you're given a word and have to find all the different arrangements that the letters can make, this is a permutation problem found by performing n factorial. The problem gets tricky when there are more than one of the same letter. For instance, the word stat has 2 T's. When the T's exchange places, we still have the word stat. Still the same, technically still the same arrangement of letters. So we really don't want to count stat and stat as 2 different words. So we need to eliminate the permutations that end up with that same arrangement again. So the formula ends up like this, where you still do the n factorial, but you look at the letters that repeat, and you see, well, how many times do the repeating letters appear? And you do those number of factorials on the denominator. And once you divide by that, you'll see how many ways you can truly do the different arrangements of letters. All right, for example, let's say you have the word TED. Thinking about TED Talks. Right here you have 3 different letters. So really 3 different letters, and you want to see how many different ways to arrange. That would be 3 factorial. How many permutations are there? I know that EDT doesn't make a real word or a real name, but we don't care. Right now we're just seeing, well, how many ways can you mix up the letters and come up with new ways to line up the letters? Doesn't have to make sense. The word doesn't have to make sense. So you got 3 factorial, or 3 times 2 times 1, which gives you 6 different ways. And you can actually promptly test that and come up with those different ways. You can say, well, TDE, you could say EDT, ETD, you could say DET, or DTE. So that's 6 ways right there. But what about Bob? Okay, different name. You should still have 3 factorial, or 6 different ways. Let's see here. B-O-B. If I switch the B's, I still have B-O-B. Let's say I put the O first, B second. If I switch the B's, I still have OBB. Or if I put BB first, O last, I switch the B's, I still have BBO. Some of these are not really different. So not the best way to do this. So according to our new formula, what it says to do is not just 3 factorial, but see how the letter B repeats? B appears twice? Divide by 2 factorial. By dividing by 2, you're going to get this down and you're going to look at, oh, wait a minute. There's groups of 2 that are basically identical. So divide by those groups of 2 and see, well, how many are truly different? You've got one group here that's identical, one group here that's identical, and one group here that's identical, but those three groups are different from each other. So you really have three distinct arrangements you can do. Now up here on TED, it still works. You can still say 3 factorial. And notice that you don't have any letters repeating. You end up with 0 factorial on the bottom. And I know this is weird, but 0 factorial actually equals 1. That's something to keep in mind. Kind of like how a 0 exponent gives you a result of 1. 0 factorial, for some similar reasons, equals 1. So you end up with 6 over 1, which is 6. All right, what if you have a longer word? What if you have something like, oh, here's one of my favorites, Mississippi. Okay, Mississippi has, what, 11 letters. But if you just do 11 factorial, you're going to see quite a few of the same words popping up. You'll see Mississippi there several times. So you want to divide by enough to, eliminate these repeated words that look similar. Just by, you don't want to just swap the I's and say, oh, that's a new word. That's just not going to make sense. So let's see what letters repeat. You have I that repeats. It appears 4 times. So you put a 4 factorial here. I think it might help when you're putting this in the calculator to think about putting the denominator in parentheses. It'll help you with order of operations. You have S that appears 1, 2, 3, 4 times. So that's another 4 factorial. You have P that appears 2 times. So that's a 2 factorial. Now M only appears 1 time. That's like a 1 factorial. 1 factorial is just 1. So you guys see what that equals. If you go to put in your calculator, put that denominator in parentheses. So otherwise, the calculator will try to go ahead and divide 11 factorial by 4 factorial and then multiply by the rest of this because it's trying to follow order of operations. But if you put the denominator in parentheses, it'll force that denominator to be multiplied together and then the division. All right, I'm going to do it by hand because I like doing these by hand because I love seeing stuff cross out. I'm a list maker. And I love crossing out stuff on my list as I accomplish it. I'm so sick, I'll even take stuff I've already done and put it on my list just so I can cross it out. I know that's weird, I'm sorry. So I'm going to go ahead and write this out while you can pull out your trusty calculator or speed up the video and skip over this part if you want. That's the nice thing about not sitting in my class is you're not stuck sitting here with me with my insanity. You can always fast forward it, but whatever. Stuff cancels out. I don't need to worry about all these ones. Honestly, you multiply by 1, it's not going to change anything. I have a 3 here and a 3 there that's going to reduce down to 1. I have a 2 here and a 2 here. Oh, let's see. 3 and 9 reduced to 1 and 3 right there. 2 times 4 is 8. That'll reduce with this 8. I got a 4 and a 4. And then I'm still left with a 2 down here. 2 goes into 6 3 times. So there I am. I got 11. And you might reduce it a little differently, and that's okay. Just once you're done multiplying, you should end up with the same answer as me. Let's see, 11 times 10 is 110, times 3 is 330, times 3 is 990, times 35, whatever that comes out to. Put it in your calculator and see what you get. I'm getting 34,650. Does that sound about right? I did try to do that in my head. So how about we double check with the calculator? Let me show you how to put it in the calculator in case you're having any trouble with that. And show, yes, keep, because I want to post those later for you. Let me pull up my calculator again. Okay, let's go ahead and do 11 factorial divided by parentheses 4 factorial and another 4 factorial. And then a 2 factorial. Do we really need 1 factorial? Not really, but I'm just going to go ahead and do it anyways. So I know you guys probably like to see everything on there to see how it's supposed to be done. But you go ahead and put 1 factorial on there. And close your parentheses. Don't forget to close the parentheses. And hit enter. And yes, I did it right. 34,650. So there you go. So now you have that information. That's what happens when you're trying to figure out arrangements with repeating, the same. Or the arrangement order matters, so still permutations question, but when you have repeating figures and swapping 2 S's isn't going to make a lick of difference, then you got to follow this formula. All right. Well, I hope you had fun. Make sure you practice, because next lesson is combinations, and it springs off of permutations. So having an understanding of permutations and the counting principle will help you when we get to combinations in 11.8. But anyways, thank you for joining us, and I look forward to seeing you again soon.